Looks like we're just about there. Welcome back, everyone. So I put down a comment right before we started. We're just about 75% done with the entire semester. Congratulations on getting through it. But really, it's almost closer to the end than it even seems like by saying this right here. Next week is going to be an ordinary week, but we may do a review on Thursday. I'll remind us all again on Tuesday about that. Then that's week 13. Week 14 is an exam week, so we lose a day on that. We'll still have a normal lecture day on Thursday. And then week 15 is close week, which means this is a entire review week. We might just finish off the last concept on Thursday of this week here, but we're not pushing into any new content whatsoever. So expect to come back on Tuesday, starting a full-on review for the final exam. And then week 16 is finals week, so we're just about done. I expect to get some specific information from the director of campus services here on Idle Falls to say exactly which room number the exam is going to be held down for the in-person section. But for the online section, thanks for representing us today, Abby. This will be pretty much just like any other exam. Information will be sent down to the Pocatello Testing Center, just like before. So we're nearly through all our content. Where we're at right now is, let's see here. It's always hard to get that back where it's supposed to be. There we go. Our sixth quiz is due today. This one's on the closed interval method, section 4.1. Our new quiz is based off section 4.4, optimization, and we're about halfway done with this section here. Well, any questions at all, folks, with the announcements or any other particular questions at the moment? Okay, so working on optimization, the problems we're about to do is going to support quiz number 7 down below right here. And here's where we left off. Just a really big white screen right here with lots of places to work, a paragraph describing something we want to do mathematically. Instructions for these last two examples is show all steps, but this time it's up to us to decide. If we feel like the first derivative test is going to be more effective, we'll use it here. Or if you decide the second derivative test is what we want, we'll use it here as well. This is about the way the actual exam question is going to be. It'll be kind of open-ended, so you can decide one route or another. But the idea with this is we want to pick the easiest test. So we'll make sure that we do that on these exact notes, make comments on why we picked which test we did pick. It's hard to say what's the best test on example 3, because there's a lot of information here of what we're meant to achieve. Find the cost of materials for cheapest container, but it doesn't even give us the function. On this kind of problem, it's up to us to build what is the mathematical function we're actually optimizing. So let's start right here on the top. The context says, we are building a rectangular storage container with an open top so that it'll be a bottom base, 4 sides, but nothing on the top. We do know it's going to have a volume of 10 meters cubed, but maybe before even that, for a problem like this, where we have to actually build a function, we want to use all available tools, and a big tool right here is, let's just draw the box. We don't know exactly what it's going to look like, but anything that organizes the information is really, really helpful. So here's my attempt at drawing a box. I'm not an artist, so this is something I literally do practice before class so it doesn't come out weird. Strategy is 2 squares about the same exact size, kind of offset like that. Then start drawing edges like this. This would be an edge you couldn't quite see until it comes over here because it has an open top. You can see this edge, and it would look about like that. It's not perfectly believable until I start to kind of come around here, bring that up. This is an edge you see all the way to that point, and then it's covered right around here. It's hard to hit. Again, this is not something I'm quite good at, but for people who are really good artists at this, it's not just about drawing these lines, it's also about the shading that makes this really convincing. So let me try one more time, straight edge, then a line going to that vertex. So this is our box. Does it seem kind of convincing just by that? Awesome. It says next, this box must have a volume of 10 cubic meters. So imagine you're just building this for someone. We're not going to ask any questions on what in the world they're doing with 10 cubic meters in this container, but If that's the case, they're talking about a volume. A volume is length times width times height. So we might as well start putting in that information. Let's see here. The length of the base is twice the width. So I drew this really long. I'm going to make this be the length, this the width, and this is the height. So we've got all dimensions represented on our box. We have the formula that we need for this, volume. If this was an exam question, I would supply that formula. But for homework questions, we might have to do some digging or research on what is the right one to match the situation. We're told volume is 10 cubic meters, so I'll just put that on the left for volume. 10 meters cubed is length times width times height. So we got through the first sentence, and then we just keep on going, analyzing this slowly, bringing in information as we see it. Next line says the length of the base is twice the width. So we want to put down something that shows that mathematical relationship. And one strategy is, we go to the width, we could introduce a new variable x. Then, if the length is twice the width, length is now 2x going this way. But there's no information on that sentence that relates the width or the length to the height. That's where we have an extra challenge. We just need to call that some other variable. Let's make this a y. So now, putting the dimensions together using that sentence, we can now substitute information for length, width, height, and get an equation that goes 10. I'll drop the units just for the moment. Length is 2x. Width is x. Height is y. So now we have an equation going, let's simplify this. 10 equals 2x squared times y. That equation there isn't going to necessarily help us find the cost of materials. It's just a required step we have to get through, because this equation is the so-called constraint. The volume has to be exactly 10 cubic meters, constrains us into this equation if the length is to be twice the width in that way. So that's one part of the problem down. Next part is this cost analysis right here. Let's leave this part highlighted. This is maybe the trickier part of the problem. The costs are different for this. Looks like the base is extra reinforced. It's at $10 per square meter. The sides are not extra reinforced, so we're probably not putting a volume or a liquid inside this volume. So all four sides just at a rate of $6 per square meter. So let's take that information and build now the cost equation, which comes from that highlighted line. So on the cost equation, this is a good one to go really slowly. Let's start just with the base at $10 per square meter. By base, we mean going this way, just the bottom. And if it's at $10 per square meter, we can say that the cost is going to be, take $10, it's per the square meter, so we find the area. It's going to be x meters times 2x meters to get the area of the base. Let's actually write that in just for the sake of saying exactly what we're doing. Area of base is going to be now, I'll drop the unit for the moment and go 10 times x times 2x. So we get altogether 20 x squared in dollars. So we have half the cost we need, the base is down. Next thing we need are the sides. There's 4 sides, so you could break this up even a little bit further. You could do, say, the front, back side, then do another line for left side, right side. But let's maybe do just all 4 at once. That shouldn't be too bad. So for the side cost, first one, let's look into the front versus the back. So this is going to be equal to, now we're at the cheaper rate, so less reinforced material, $6 per square meter is going to multiply. First, we're considering the front and back side. So the dimensions that are relevant here are the width and the height, just those two dimensions. But because there's 2 sides we're tracking, we'll go 2 times to start. Then put in width times height, so x times y. So that takes care of front and back. Let's do another one just like that. So let's see if this color coding kind of stands up. Let me know if this looks just a little too much stuff going on. Here's the left side. Let me say that better. Here's the left side. Here's the right-hand side. So this is going to be left, right sides. And now let's analyze what we would be doing in that case. If we're doing the left side, right side, this time the length is relevant and the height. So we'll use those dimensions. Like before, there's two sides we're dealing with at once, the left and the right. So we put in a factor 2 to start. Then multiply by the length, 2x, multiply by the height, y. Now we have the area of that side, just this one, and the factor 2 gives us areas of both sides. So front and back, left and right is a little bit more annoying to put together, but it really just comes together the same way the base did. We found the area of the base, then we just multiplied it by $10 per square meter. So simplifying this one down, this is going to be equal to 6 times 2xy plus 4xy. That means we have like terms inside that bracket. It's 6 times 6xy. And then finally, altogether, this is 36xy. That's a lot to get started on a problem like this one, but we're getting there. So far, we have a base cost, $20 x squared, and we have a side cost, 36xy. We want to put all that together and now find the cost of the materials for the cheapest such container. So we need a new function that's going to take this component. We can call it total cost. Let's write it in here. Total cost. We can make this be, say, C. C is a function that depends on x. And next thing we can write in is that C of x is going to be cost of the base, 20x squared, plus the cost of all 4 sides is 36xy. And now we're starting to get there. Let's just add a little bit of a reminder where these came from. Left, right sides is that term, and front back is this term. Well, definitely kind of an annoying problem in a certain sense, right? There's a lot of little components to get through here, but it's a great problem because this is just a way to maneuver through a bunch of information given to you verbally, actually build out a structure, work through the information to finally build the function. So a lot of analysis goes into this kind of problem, but makes it a pretty honest mathematical application problem. Sometimes this is how the applications actually come in. We do all the dirty work to build in the function we're even optimizing in the first place. Any questions at all, folks, to this stage?
I do have a question. For going from the very first, figuring out the constraint, the equation prior was 10 equals 2x times x. So how come for a constraint, we don't combine the exponents for the 2x to equal 2x squared for the constraint?
Yeah, that was my mistake on there. Thanks for spotting that so much, Abby. So just like Abby said, with this x right here, let me put it in red to highlight my own mistake on that. And that x, I should have combined into, exactly as you said, 2x squared on that one. Let me write that out in a little bit better way. This should have came out as 2x, and again, good eye on that exponent, 2x squared times y. Phew, without that squared there, there's no way we're going to get the right total cost on this thing, because we have to use a constraint equation to replace y, and without that power 2 there, highlighted in red, we're going to be way off on our total cost. So you've pretty much saved the problem with that observation. Thanks for spotting that. Other questions at the moment? Okay, and again, this is kind of like the very first problem where we want a function of one variable x because that's what all of our methods are based on in this course. So the fact that we have a y still here is not good for us. We need to take this y represented here, and from the constraint equation, solve for it to substitute back. So for the moment, let's go back to constraint. Equation says 10 equals 2. Now x power 2, thanks again for finding that missing power, times y. It's a quick solution. We'll just divide both sides by 2x squared. So this implies y equals 10 divided by 2x squared. Let's simplify this a bit because we have to throw it back into the equation right up here in blue. This is going to turn into 5. I'm going to write this in as x powered negative 2. Make this differentiation a little bit easier. So from the constraint, the fact that the total volume of this box has to be 10 cubic meters, we have a new relationship for y that pulls in the variable x. So now the total cost really is a function of one variable. So here's our next step. Total cost is now better defined as c of x equals 20x squared plus 36x times, now the y variable, 5x powered negative 2. This is a good opportunity to take a look into a calculator. I need to do 36 by 5 at some point. So we'll get 180 from that part right there. So next line, total cost c of x is 20x squared plus 180 x power negative 2. Now the whole method is ready to start. We can begin optimizing because we have an honest function of one single variable x, which takes into account the applied problem in the background right over here. Also, let's keep in mind that a lot of our methods depend on a domain. There really is a natural domain right here because once we say width is x, we're also saying x is greater than or equal to 0. So this is placing a domain on our actual function. You might feel like that's a weird domain though, because if I say greater than or equal to 0, equals even 0 would mean we don't have a box at all. So maybe we should fix that just a bit to match the reality that we're trying to build a box and really make x be strictly positive. This allows it to be infinitesimally small, but never 0. So there is always a box in the background. And that means down below here, we can say domain of C is, we use interval notation, 0 to infinity, or if you prefer, x bigger than 0 captures that same domain. Now we want to decide on a method. But the observation here is the second derivative is extremely fast on this one. So second derivative test would be the best choice. Let's write that in as a comment because that is part of the concept when we do this as an exam question. Always really smart to try to pick the method that seems to fit the best. And here, second derivative test should be used. I can't say must. If you use the first derivative test here, works out just fine. You might take a lot of extra steps because of the interval estimates. So I'll just say here, second derivative test is faster, so it should be used. And we're just learning that method, the second derivative test. So let's actually go up here, grab the whole thing, and work through our methods while looking into that definition. Okay, so here's our next step. We have a function. The second derivative test says, what are we doing? We're not maximizing cost. We're trying to minimize cost for the customer. So that means we want our second derivative to be positive, and it needs to be positive for all x in the domain being non-negative values for x. If we can make that happen, our job is essentially done. Yeah, go ahead.
Wouldn't that be x be a negative 1 or 180 x?
Oh yeah, thanks for spotting that. I've been struggling today with my exponents, it looks like. X times x powered negative 2 absolutely is x powered negative 1 right there. Thanks again for spotting those weird mistakes, folks. I think I'm just tired getting to the end of the semester. So those combine as x power -1. And with the help of everyone in the class so far, we've got our actual accurate cost function. Other questions at the moment? Okay, usually when you're tired, it's arithmetic that's the first thing to go, but it looks like my algebra part of my brain is shutting down at the moment. So thanks for your active participation on those small mistakes here with that power 2, and here combining x by x power -2. Other questions at the moment? Okay, now we're in good shape to begin the method. Let's call this step 1, which seems kind of crazy when you think of it because we took all of these steps, but those were steps to get the function itself. This is step 1 for the second derivative test in particular. Step 1 is going to say, differentiate your cost function. So here it is on this line above. Derivative is rapid, 40x minus 180 x power -2, with a correction on that power here. The -1 would multiply 180 for a negative value, and the power goes down by 1, now power -2. Step 2 is all about now finding a critical number. So we want to set this equal to 0 and solve it. Let's do just that. C prime of x equals 0 implies 0. Let's write it this way. I'm going to write it below. I think that flows a little bit better. In place of where C prime of x is, put in 40 x minus 180 x power -2, and now it's set to 0. Let's see here. One way to solve this equation could be just multiply both sides by x squared. So here's x squared multiplying on the left, x squared multiplying on the right. If you distribute x squared through, let me be really careful on my exponents here, we get 40x cubed minus 180 x power 2 times x power -2 is just a 1. That's why we chose x squared to multiply both sides on. Right-hand side is still 0. The all-important 0 wipes out everything through multiplication. Now this equation is a little bit easier to work with. We could add 180 to both sides. Divide both sides by 40. That's a calculator job. So we've got 180 by 40, giving us an even 4.5. Let's use that decimal number since it's exact. X cubed equals 4.5. Let me see if I can get extra space here. No, I think we're at the whole limit of it. Now take the cube root of both sides, and x is going to be equal to cube root 4.5, and this is in meters. Recall x was just the width of the box that we're building originally up here. It's also easy to forget the context of all this once we abstract away down to just the function itself. So now that exact length, let's just figure out what that is. 4.5 power 1/3 looks like about 1.65 meters. Again, humongous box. But this is the critical number of C, the cost function. Once we get a critical number, the next step is, well, we take the second derivative and we hope the second derivative is going to be positive. That part right there by the red dot doesn't pan out. We now need to divert into the first derivative test. So let's see what happens. Here's step 3 of the second derivative test. Next thing we do is go to the first derivative and just differentiate it again. So we need the higher order derivative. C double prime at x is going to be equal to 40 on the first term. Differentiating this twice 180, it's -2 times -180 gives us positive 360 x power 1 less, so now power -3. Now when we look into this, we need to show the second derivative, our second derivative is C double prime, is positive, and we mean for all x in the domain. That might be concerning because if x is -1, whole thing is negative, But actually, it's not a problem because recall the domain is positive values of x. X is a side length. And if you're only putting in positive numbers right here, this in fact is strictly positive. So we can now say that this is greater than 0 for all x in 0 to infinity, which is the domain of C. So that means our job is essentially done. Second derivative test says f at C, the critical number, is at absolute minimum. We'll just say at step 4, let's double check. Sometimes these problems just want the critical number. They might say, state the side length that leads to the minimum cost. Other times these problems want the minimum cost, the actual y value. So we have to reread the request of this problem. It says, find the cost of materials for the cheapest such container. That means we need to take our critical number, cube root 4.5 meters, plug it back into the cost equation, and report that that's the absolute minimum cost. Supported by the second derivative test right down here. We have an absolute minimum because of the positive sign right here. So step 4 is just an ordinary conclusion. We'll say the minimum cost. We're not concerned about the volume. We're not concerned about the dimensions. We wanted the cost. The minimum cost will be C of, plug in the critical number, cube root 4.5, highlighting just to show where all those components go. Then cite your original cost function. Cube root 4.5 is going inside there. Let's show that just for the sake of clarity on the notes. 20 cube root 4.5 power 2 plus 180 cube root 4.5 power negative 1 is going to be equal to, in dollars, let's cite Desmos on this one. So 20, putting in a cube root of 4.5 is really awkward in a calculator like this, but we can use our knowledge on exponents to say this is really just to the power 2/3. The index here is just the denominator in the exponent. So to power 2 over 3, we're up to $54, but then add this part, plus 180 times 4.5 to the power. This will be negative 1 divided by 3. Negative 1/3. So we have a total cost, natural place to round is the nearest cent, of $163.54. We're definitely not building this out of concrete, but they get a box and we have a cost estimate. 163.54. That barely fit the page, but we got it, folks. This is the analysis for something more in like a business type of application, trying to optimize cost by minimizing the cost of a product. Any questions at all on this total analysis? Yeah.
So why did you drop the y for 36 x y again?
Let me double check. Oh yeah, this line right here?
Yeah.
That's because when we go to take the derivative on this line, if the derivative involves x, then we have to get rid of that y right there.
Oh.
So it's only, exactly, we took this right here and then substituted it into that position, getting that result down below. Other questions about that so far? Now that we see the total end to this problem, one thing I could say to allay some potential fears, I don't think this makes a good exam question. This is a question where you have to have a lot of extra time, a lot of mental space, not the pressure of an exam, timed exam looming on us. This is a great homework question, so you should expect to see something like this as potential quizzes, a potential WebAssign problem. But as an exam question, I would rather do a problem that looks more like this one, because we don't have the mental space to do all that extra problem solving to build the function. Exam question will give the function. Our job is just to optimize based on it. But we still did a problem like this one because it's valuable. It's a realistic and honest application type problem, and it supports the homework as well. So let's give our try on the last problem in the set down below. Example 4. We've looked into a function briefly along the lines of something about like this. This is now an application in the so-called pharmacokinetics discipline, where we're wondering, how does a blood react on human biology? Oftentimes we have something called a surge function. That's what this one is. That describes the drug response in some kind of human biology, maybe animal biology, perhaps. I'm not sure why I put a border there. I think I was going to bring in a test on this one. And actually, yeah, let's bring that border back in and bring in a test. Already looking into that function, first derivative is not bad because it's a product rule, but that is some good work there. Second derivative is a product rule again, and it starts to get messy after that. This is a problem where the first derivative test is a natural choice, because after doing one derivative, you might as well just end it there without trying to get to a second derivative that you have to prove positive. That can get really nasty if you're using product rules, quotient rules. That estimate becomes difficult. The only reason it was an easy estimate here is we happened to know something about X that made it work. So let's grab first derivative test on this one. We'll place it right above just so we can work through it as we go. This is a particular kind of first derivative test where we want to show that there's exactly one critical number. Okay, so just looking at the function, it kind of indicates this is a good route to go. Now let's run through the information. The context says blood alcohol level in milligrams per liter of blood, T minutes after consumption of a hard liquor is given by the surge function below. So human biology is interesting. This is not necessarily saying this is going to happen to anybody who takes however much hard liquor was in that one shot, but this is more about averages. The average of human biology, say in a particular country, they might be able to find that kind of information and model it in this sort of way. And now we wonder, at what time is the blood alcohol level at its peak? Which is kind of a natural question, right? You can imagine people experimenting with this just by going on a feeling, but we want to model the actual blood alcohol level in the body. Here's the model as a surge function, and then just see where's the optimal value on that. So that will give us a time the blood alcohol level is at its peak. That means this problem ends the moment we find the critical number, prove it leads to an absolute maximum. We're not looking for the blood alcohol level. That's the output to the function. We're just looking for the input, the time. We won't round any intermediate computations. This is important WebAssign, especially since often they want exact answers. And even if they're asking you to round to 2 decimal places, we'd only want to round at the very end. Rounding in the middle could actually throw our answers off a lot, especially if there's an exponential function in the mix like this one. So here's how it starts. Kind of a nice problem when you think of the last one. We already have the model, so we begin just by differentiating it. It's called a step 1. B prime at t. And it's a good review as well. This is a product rule problem, so let's analyze it in the typical way. I'll keep the constant together with t, so I'll write in 26.9 t prime times e power negative 0.11 t plus, this time we're copying 26.9 t, and this time we're differentiating e power negative 0.11 t. So there's our product rule indicated. This derivative is nice. This will just be at 26.9, so let's write that in. 26.9 here, upon differentiating, times e power negative 0.11 t, plus, just copying through here, so far so good, 26.9 t, then multiplying this derivative. This is kind of an infamous chain rule. The most chain rule questions that come to me are usually based off functions like this, an exponential, maybe a logarithm, maybe it's 5 to the power of negative 0.11 t. These usually are the tougher chain rule problems. In view of that, let's take our time with it. When you see something indicated this way, not a bad idea to think mentally that there's parentheses right where the t value is, the exponent position, because this kind of indicates you it's like an f of x, and that's the input, the x. That means it's the inner function, and the outer function is an e power x. Well, the variable is actually t, but instead of t, we had negative 0.11 t. That's why the chain rule is being called. Base the exponential is our outer function. So here's how the chain rule starts. Essentially every single time we used it, except for maybe on Tuesday, I think we did it in a more streamlined way. But this is the full method. You would take e, let me drop that parenthesis there since we're officially differentiating, we can drop this parenthesis. E to the power of something times the derivative of something. This is how we indicated it each and every time. The only thing that's different is the format of the function. It's e to the x. We put a placeholder right here where the exponent is. Then we come back here to the inner function, plug it into the first open parenthesis, negative 0.11 t, plug it back into the second one, negative 0.11 t here, and that's our last derivative to take to finalize the full method. This is meant to be a multiplication symbol, not a decimal point. Let me raise it up a little higher. So next line, b prime of t is 26.9 e power negative 0.11 t plus 26.9 t here. And when I differentiate this part, when we differentiate it, t just falls off and we get the slope of the linear function, negative 0.11. This is totally finalized, so I'm going to copy it in at the last spot, e negative 0.11 t. Parentheses are just to show the structure, so we can drop them on this line as well. Now you can see why we said first derivative test is probably a good route. We're not even completely done with this. We'd probably want to factor it up a little bit, multiply the constants together to simplify it. If we were doing the second derivative test, we'd have to gone through this again on the second derivative. And the second derivative is harder than the first one. It's a lot of extra work. So sticking to first derivative test, if you're taking a lot of steps just differentiating once, that's the good test to go on. Next thing we can do to make this a function that easy to work with, factor out the greatest common factor, e power negative 0.11. You know what, we can factor out maybe even a little bit more. We have as a common factor 26.9 e power negative 1 t. There's 26.9, but we have to leave the t behind, but also factor e power negative 0.11 t. So 26.9 e power negative 0.11 t leaves behind, on the first term, just a 1. We took out everything. Plus, on the second term, this is gone, but t survives, and so does negative 0.11. That informs me we should actually go minus 0.11 t. Does that make sense to folks on the factoring step for this one? Okay, let's now continue on with this. Let me drop that below where it's out of the way just for the moment. This really takes us to, I'd say, a firm step 2. Step 1 for either method is to find the derivative. Step 2 for either method is find the critical number. So we take b prime of t, set the whole thing to 0 and solve, which means we're setting all of this stuff equal to 0. So 26.9 e power negative 0.11 t times 1 minus 0.11 t is set equal to 0. Because we're careful to factor, we can now split this equation into 2 of them. This implies 26.9 e power negative 0.11 t is 0, or 1 minus 0.11 t is 0. So those are our next 2 equations to solve. Now, this is a bit concerning because if you have 2 equations to solve, it means there could be 2 critical numbers. But we kept saying all along in these notes, there's got to be exactly 1 if this test is going to work as intended. But here's the one that doesn't give us a solution. Here's the same issue we've been encountering over and over again. E power A is bigger than 0 for all A. Doesn't matter what number you pick. So the first factor here by the red dot is positive. So is the other factor over here. That means we'll never hit a 0. This one has no solution. Thank goodness, because we do get a critical number solution over here, and that's the unique critical number that we're expecting. So let's add negative 0.11t to both sides. Or let me say that better. Let's add positive 0.11t to both sides. We get 1 equals 0.11t. Divide by 0.11. That's not part of my repertoire. That's a weird division. Let's go 1 divided by 0.11 in the calculator. And there's got to be some information on rounding. We're going for 2 decimal places. This is time, so 2 decimal places makes a good amount of sense. We'll say 9.09 minutes. Equals t. And the moment we found that, this concludes step 2. Well, all we wanted was a critical number, and that's what this is. The critical number of B, the blood alcohol level. So this is suggesting if there is a spike of maximum blood alcohol level, it should happen at 9.09 minutes. But we have to be really careful with that. We now have to actually directly use the first derivative test and show it really does lead to a maximum. So this is where step 3 occurs. And it's the reason why we try to use the second derivative test when it does work, because this is a lot of work on the next step. So step 3, every time we've used the first derivative test, what we did next was consider the domain of the function. T is greater than or equal to 0 on this one, because it's equal to the minutes after the first or the one shot of the alcoholic beverage in this particular problem. So it does make sense it could start at 0 minutes. That's the instant we'd say the shot was consumed. And we're concerned what happens thereafter, so positive. So with that information, our number line should really look like this. Starts at 0 minutes. This is t minutes after consumption. It pays to be kind of descriptive on your horizontal axis for any kind of applied problem like this. Just connects a lot of dots in our mind on what we're actually doing on that step. Throw down the critical number that we found. So 9.09 would go here. Then we now have 2 regions that we have to test the sign of the first derivative on, b prime. If everything is working as intended, we should be able to show we're increasing here. So blood alcohol levels going up after consumption, hits a peak for 9.9 minutes, and then it should be going down. So that's not a guarantee at all. The model itself could be just misconfigured. We could have made a mistake in some odd places. So this is something we directly resolve ourselves. Here's the derivative b prime of t in its simplest form for this task. We just need a good critical number. Or excuse me, a good test value is a better way to say it. Let's test right at 0. It is in domain, so that's allowed, or 1 would work as well if you like. But I want to test the value 0 itself. So here's testing for b prime sign. Go b prime at the input 0 minutes. We did that. Here we have e power 0. That's just a 1. So 26.9 carries in. Then here we'll just have 1 minus 0. And that really is a positive quantity. So we have greater than 0 there, which means we can put in greater than 0 right next to this b prime, and this entire range until the derivative goes to 0 at 9.09, we have blood alcohol level is increasing, referring to now just b itself, the original function. Then we just test it again on another value. 10 minutes might be the easier next value to put in. But any questions with the logic on the first test value? Okay, Nearly there. Let's plug in 10 minutes and see what happens. At 10 minutes, we're doing B prime at t. So come back over here. We'll have 26.9. Putting in 10 there gives us e to the power of negative 1.1, but still positive. Face the exponential, never will go to 0 or be negative in this form. We're plugging 10 right here, so this is 1 minus 1.1. And sure enough, that's a negative value, 1 minus 1.1. The values in front are all positive, even with the negative exponent on me. So we have a positive times a negative. The whole thing is now less than 0. So coming back here, increasing decreasing test tells us if the derivative is negative on this range, it must mean that B, what I'll call level, is decreasing. So the person's sobering up after the 9-minute mark. Maybe not rapidly, but it is occurring. Well, we're done at that stage. We show that the function is increasing. That's this part. Let's see here. The derivative f prime of x is bigger than 0, so increasing for all x less than c. Well, its t value is less than the critical number, but they're referring into this range. The next it says the derivative, visualize that as a b prime of x is negative for all x bigger than or times c, 9.09, referring to that range. And everything does in fact check as true when we compare this against that line. So step 4 is just concluding. We can now make a strong conclusion and say blood alcohol concentration is maximized at t equals 9.09 minutes. So if your friend takes a shot, you know you have about that much time before some really noticeable behavior changes, probably sooner, but that's when it peaks. Any questions at all, folks, on getting through this problem here? Okay, so that's our last optimization problem. It turns out the quiz that I assigned is pretty similar to this one. And my goal with assigning quizzes is really just to give you an opportunity to practice problems that make really strong candidates of real exam questions before you have to take that exam. So it's kind of a giveaway on the exam as well, but essentially what I'm saying is practice quiz number 7. You'll get some great feedback on how this one goes before exam 2. Take a look at that feedback, and if you understand why everything went correctly or why something might have been missed, then you'll have really excellent preparation. What I do agree is a difficult section on the second exam, or excuse me, third exam. So this one's pretty similar, but this is about a predator-prey population. Size of predator population is going to be P, indicated by this model. And the population of the predators will fluctuate based on the prey density X. Maybe it's something like, say, wolves and rabbits. The wolves would be P, the rabbits would be X. Notice that's also a search function. So a first derivative test would be a good option on this one. That's why it's highlighted right here. But if you did go second derivative test and your steps are correct, I would take that as an answer too. It's just a lot of extra steps. Well, we got through an infamously tricky section, the optimization. Now we're going to go for the antiderivatives. Even though this is still in chapter 4, really this represents us turning over into chapter 5, taking a look at integration with the last amount of time we have in the course. Before we move over to that next section, any last questions or comments about the optimization? Okay, let me close this out. And we're nearly done. Next one we'll take a look into. They said they're going to upgrade our computers over the summer, so hopefully this stuff runs a little bit better. I can really tell we're pushing Microsoft Word really hard for this class, it seems like. So now we're dealing with a kind of a weird, mysteriously titled section called antiderivatives. Goal here is to try to unwind what we've been doing all along, starting in chapters 3, chapter 4. We differentiate something. We wonder, how do you reverse the process? If we can discover what that is, we'll be getting into integration very shortly. So here's how the definition goes. And this color coding I'm going to maintain really, really accurately throughout these notes, just to show the relationship between the antiderivative and the given function f. So the relationship is f is an antiderivative of the lowercase f function if the derivative of f results in the given lowercase function f of x for all values x in the interval where f is defined. Kind of a strange definition. The best way to learn it is practice with it immediately. So here's our two practice runs, part A and B. We've got a function f of x defined to be a fifth degree polynomial. So given lowercase f of x is a fourth degree polynomial, and we wonder, is the derivative of f lowercase f of x? Plausible, because if we differentiate this one, the degree does go down to degree 4, and the derivative of 2x power 5 is 10x power 4. But that's just checking against one term. The method is really take the function f, differentiate it immediately. We're on this line of the definition, and then just check, does it equal lowercase f of x? So checking if you have an antiderivative is just differentiating as normal, but you have to know which function to differentiate. That's the major thing. Derivative of this function here as a polynomial is 10 x power 4 minus 6x plus 2. Now we wonder, is it equal to 10x power 4 minus 6x? Not quite, right? It's really close, but it's off by a positive 2 right here. So we have to put not equals. Then we go to this part of the definition, and the major definition check is, do we actually have equality there? If so, we'll say yes, uppercase f of x is an antiderivative. But that didn't happen with not equals. The immediate conclusion is f is not an antiderivative of lowercase f. Here, we're just referring to the name of the function. That's why I wrote uppercase f of x and lowercase f of x here. So without that relationship holding, we don't have a proper antiderivative. But that's good, that's important. It's good to know when you don't have an antiderivative. Probably in part B, this f really is an antiderivative, so we'll check that next. But any questions first, folks, on the part A? Okay, let's try this out again. So new function f, that's the one we're testing if it's an antiderivative in blue. Lowercase function f of x is just natural log x. So if we differentiate this and get exactly natural log x, we have an antiderivative. So let's begin with derivative here. F prime of x is going to be equal to, this part is product rule. So let's carefully write out steps on product rule for this one. That's going to be equal to first derivative of x. If you put in a 1 here, that'd be totally fine. For the notes, I'll write this in again as the usual structure we put down. That x times derivative of natural log x. So everything I've written down so far is just the derivative of the part in by the red dot, product rule on that term. Move over to this term. We also differentiate it right on this line. But derivative of negative x is -1. So nothing further to say on that one. Now back down to here, differentiate as normal. X prime is a 1. So it's 1 times natural log x. Moving over to here, copy an x. Times derivative of natural log x is just a 1 over x. -1. Let's keep going. There's still stuff to simplify. This equals natural log x. X by 1 over x is a 1. But then -1 gives us like terms, and this is now equal to let me write it this way. This is now equal to natural log x. So with the direct equality right there, what we just showed is the derivative of f is lowercase f of x, because lowercase f of x is defined to be natural log x itself, the result that we got. So the equality right here is the only thing that tells us once and for all, f is an antiderivative of f. So that's our check on that one. Any questions at all, folks, with the example 1 so far? Okay, now what we did in this problem was just verify that we have an antiderivative. What we want to do next is actually find the antiderivative, but maybe let's look into one more concept, part C, before we look into what we mean by the most general antiderivative. The idea here is, once you have an antiderivative, you in fact have infinitely many antiderivatives all at once, which is kind of weird. But here's the thought. Add an arbitrary constant c. That could be 2, it could be 5, it could be 0. The derivative of 0 is 0. But we want that just to be some arbitrary constant, any real number. Now, if we go to differentiate the f of x again, here's what it would look like. F prime of x equals, we've differentiated this part already, right? Derivative of x natural log x minus x turns into natural log x. So we don't have to redifferentiate that again. That's kind of like reinventing the wheel. But we can differentiate that part. That's a constant, just like any other constant, like a 5 or e to the power 2. Derivative of a constant is always 0. So we go plus 0 on that derivative. And then this gets us, that's equal to natural log x again. So coming from that f of x, due to this equality, we now know that f is still an antiderivative of lowercase f of x. And it didn't matter what was in here for c. This could have been plus 5. Derivative of x natural log x plus 5 is just natural log x plus 0. So now we say, well, any constant like that works. Just put it in this way arbitrarily. And this is what we mean by the antiderivative. So let's call it that specifically right here. Notice over here, f of x is a antiderivative. We use the indefinite article because there are many such antiderivatives. But this one is referred to as, because of the constant c, the antiderivative of f. English majors probably don't like that either, though, because I use the definite article to say there's only one, but that's infinitely many antiderivatives. What we really mean is this is the form that the total answer would take when we use the definite article right here. So this is how we get our antiderivatives. It turns out our antiderivatives, for trying to find them in general, always have that arbitrary constant. It's an important feature of the problem to give the full answer. And that's what the next part is all about. So restatement of the definition down below of what an antiderivative is. It's a function who, when upon differentiation, gives a lowercase function f of x. And if f is an antiderivative of f, let's write this in with our color coding. Take f to be an antiderivative of f, then its most general antiderivative is going to be, take your f of x, add the arbitrary constant c. Again, it's any real number. And the slight comment down below is saying, anytime we're going for an antiderivative, the assumption is implicit that we're looking for the most general antiderivative. So we'll always add in that constant c right there. That's a lot of information so far. Any questions at the moment? Okay, these notes are kind of short, but that's because it's kind of packed with a lot of interesting information. We want to take our time with this because finding an antiderivative is one of the major steps when we go to integrate with the fundamental theorem of calculus. And it just so happens, the very first part A right here is hugely important for finding antiderivatives. Let me show you what I mean by that. When we were in chapter 3, say section 3.3, looking into nice formulas for differentiating without using the limit of f of x plus h minus f of x over h, we mentioned that there is one formula that seems to be the most important one just because it's used so much, and that's the power rule. The power rule states the derivative with respect to x of a function like x power of n always goes like this. Let's analyze this in terms of steps. First, write down the formula. N comes down, but that's a step 1. Step 2 is that you multiply. Then you do put in x, and I'll call this a step 3. You reduce the power by 1. So that's the whole logic of the power rule. Drop down a coefficient, multiply, reduce the coefficient by 1. Now, over here on the left, this is a function f of x, but what we want is the antiderivative, f of x. This is a total reversal of our differentiation formula. Everything about it, even the order that you take these steps. Turns out the very first step now is, well, we don't drop the power, we increase the power. We do the opposite thing. So we'll go x power n plus 1. In the antiderivative, later on we'll say when we integrate, power goes up, and when you differentiate, power goes down, because now they're totally inverse processes. So this is the step 1 this time. Once we get that power in the right position, step 2 is not to multiply. We do the inverse thing. We're dividing this time. So now we'll go times 1 over the fact that we're dividing right here is step 2. Dual to this step 2 in the middle where we're multiplying. And the thing that we divide by is the new exponent, n plus 1. N plus 1 goes down below. And this is step 3. So this is really a whole formula altogether. And this feels kind of silly in a way, but keep in mind that plus c is actually really important. We still have to put in plus c to make this a general antiderivative of the power function x power of n. It looks weird, right? But the nice thing about this whole set of problems is you have some powerful methods to double check your answer every single time you come up with an antiderivative. The check looks like this. Take your f of x and just directly differentiate it. If we've got the right antiderivative, we need to be able to differentiate that thing to come back to the original function f of x. So imagine this is just some unrelated problem we're differentiating. That's a constant. Or is it? Let's think about this a little bit harder. Although the power rule works for every single power of n, there's no problems whatsoever. Reversing the power rule actually does have a problem. That right there can't be 0. So implicit in this entire problem is, well, n cannot be -1. We need a second formula if n in fact is -1. That's kind of surprising in a way. Because if n is -1, then we'd be raising this by 1. It's now power 0. We divide by 0 right there. Very concerning. So let's write that in as an assumption, and then we'll fix it by doing f of x again when it exactly is -1. So with that check, let's get back on track here. This is a constant because we forbade it from ever being 1/0. It is defined now. And that means the constant multiple rule takes over. This is 1/n plus 1. Stays exactly where it is. We're following now next the power rule. First step in the power rule is whatever the power is comes down. N plus 1 comes down. Step 2 in the power rule is now you multiply by x, where we drop the power. So if it's an n plus 1, it goes down by 1. It's now just power n. Derivative of a constant here goes to 0. And this stuff here just cancels. So f prime of x is just x power of n, which directly equals f of x as required. At that point, the check is complete. We really do have the antiderivative, but we had to bake in a condition. This is really very weird again. Power rule never fails. Any value of n, no matter how weird, it could be square root of 2 times e, it still works. But the antiderivative doesn't work at every power of n. There is one exception. Let me scan through the notes quickly to see if I find it. There it is, it's part e. Because that's such an interesting exception, let's actually bring part e up. Do it right here. We don't do this often, but I think it's a good time to do it this one time. We should do this one right away, very next, to connect the dots of what went wrong over here. And the way it connects the dots is 1/x is x power -1. So we are directly looking into that oddball case right there. So next one, antiderivative of 1/x. This one's really confusing, but anyone happen to know the answer? The answer is totally surprising. So if you're not sure, I totally understand. I don't think I would ever guess this. So what we need to do is go back to even before spring break, I think it was, into section, yeah, this was before spring break. Go to section 3.7, derivatives of logarithmic functions. And there's exactly one tool in here somewhere that's going to give us the answer. It's actually way down in the notes. It's this. We have a theorem that tells us the derivative of the natural log x in absolute value is 1/x. That's relevant to us right now. So let's take this theorem and cite it directly in our notes. And it's just a helper concept before we do part E. So with that big theorem, we can now say, if this is your f of x, it will immediately imply the antiderivative uppercase f of x. Well, if I differentiate this, I get 1/x. That means the antiderivative is natural log absolute value of x plus a constant. The idea here is, for doing an antiderivative, we just totally reverse the formula. Not a total reversal, we have to also add in a constant, so it'll look like this. Natural logarithm in absolute value plus a constant. So this is the antiderivative of f of x, which makes whenever 1/x comes up, an exceptionally tricky problem. If it was a 1/x squared, that's not a big deal. Let me show you what I mean by that. If f of x is 1/x squared, you can just turn this around to x power -2. Then f of x, following the method we took before, would go like this. Antiderivative of x power -2 would give us x power -1. Then we would go 1 over the new exponent -1, giving us -1/x. So the antiderivative of x power -2 is that weird 1/x with a negative sign. But that whole method fails right on this one. And it's all because, again, if we increase the power by 1 and it was a -1, we would have divided by 0. So the logarithm is a one function exception on the actual reversal of the power rule. Very, very weird, but this is the reality of mathematics as it sits so far. Any questions or comments at all, folks, with this weird formula here? Okay, so let's put this in a box just as an extra statement to make on this. This right here is on its own and important formula. The formula says the antiderivative of 1 over x is the natural logarithm of the absolute value of x. And just as important is this one right here. So this one is an important formula as well, because it tells us we have x power of n, critically n is not -1. This formula represents the literal reversal of the power rule over here on the right in purple. So we've got some really important main tools. We can now find antiderivatives of x power of n. At any power, there's just a weird exception when it's power -1. So when we come back on Tuesday's class, these problems will be a lot easier to deal with, especially that one, say. Our job is just to collect some methods and techniques before we turn this around and use this as a tool for integration. But any last questions at all, folks, before we call it a day? Okay, well, have a great weekend, folks. Any questions come up while you're over the weekend, I'll be happy to help. And like I mentioned before, over this weekend, starting on Friday, but probably continuing through the weekend, I'll be updating information here. First thing I want to put down is the formula sheet for exam 3, so you're informed what's provided. Have a great weekend, folks. I'll see you all next week.